In this video, we will learn about the prisoner's dilemma in game theory and how to find out the Nash equilibrium and whether the Nash equilibrium is Pareto optimal outcome in this case or not. Okay, so suppose two persons A and B suspected of robbery or arrested. Okay, so we have two persons, person A and person B. They are arrested for robbery. Okay, they are the suspected one. Police have no evidence to convict them, so they are put in separate cells. So person or prisoner A is being put in separate cell, and also person B is being put in the separate cell. They cannot communicate with each other. Okay. So police offers them a deal. The deal is if both confess, both go to jail for 3 years. Okay. If prisoner A confesses and prisoner B confesses, each gets a sentence of 3 years. That means person A gets 3 years of sentence and person B also gets 3 years of sentence. Another situation is if one confesses and another denies, the confessor goes free because he becomes the state witness and other goes to jail for 6 years. Okay, if one confesses, let us say person A confesses, okay, and prisoner B denies, in this case prisoner A will go free and person B will get a sentence of 6 years. And same is true for prisoner B if he confesses and prisoner A denies. If both deny, both go to jail for 1 year. If both the prisoners, prisoner A and prisoner B deny, both go for jail for 1 year. Okay, we are supposed to find out the Nash equilibrium in this case and whether the Nash equilibrium is Pareto optimal outcome in this case or not. Okay, so when we write it into the matrix, we have prisoner A and prisoner B. Okay, so prisoner A has two strategies, either to confess or deny, and same is true for prisoner B. He can confess or deny. Okay, so if I put this into this matrix, so these black numbers denote the payoff for prisoner A, and the red numbers denote the payoff for prisoner B. Okay, so first thing is we need to find out the Nash equilibrium in this case. By Nash equilibrium, what we mean? Nash equilibrium is a situation when each player chooses an optimal strategy given the other player also, chooses his optimal strategy. Or we can say it is a state or a state that gives players no incentive to deviate from their initial strategy. Okay, so the and we can show it on this matrix. Nash equilibrium will occur when both the numbers in a cell are what we call circled or underlined, and I will explain it here. Let's take the case from the prisoner A's perspective. Okay, what happens if prisoner A confesses? Okay, when prisoner A confesses, prisoner B has two options, either to confess or deny. Okay, so confess gives him 3 years jail, denying gives him 6 years jail. So obviously prisoner B will try to maximize his utility. So since 3 is negative 3 is greater than negative 6, so he will choose to confess also. Okay, when prisoner A confesses, the best the best strategy for prisoner B is also to confess because minus 3 is greater than minus 6. Okay, similarly, let us say let us see what happens when prisoner A denies. Again prisoner B has two options, either to confess or deny. If he confesses, he gets a payoff of 0, that means he gets free, and if he denies, he gets a 1 year sentence for in jail. Okay, obviously he will choose to maximize his utility here. Okay, since 0 is greater than minus 1, so he will choose. Okay, so I will choose also to confess here. So from person A's perspective, okay, prisoner B will choose to confess regardless whether prisoner A confesses or denies. Let us see this scenario from prisoner B. When prisoner B confesses, again prisoner A has two options, either to confess or deny. Confess gives him -3 and deny gives him -6. Since -3 is greater than -6, so he will choose -3. Okay. Similarly, if prisoner B chooses to deny, again prisoner A has two options, either to confess or deny. Confess gives him 6 years into jail, and denying gives him 1 year into jail. Obviously, he will, choose to maximize his utility in this case to minimize the jail term. So he will choose -1 because -1 is greater than -6. Okay. So here you can see only cell where both the numbers are underlined. So this -3 is the Nash equilibrium in this case. So the Nash equilibrium here is when both confess, C and C, when both confess, this is the Nash equilibrium here. Nash equilibrium. Okay, by Nash equilibrium, as I have told you, it is a situation when each player chooses an optimal strategy given other player has also played his optimal strategy, or it is a state that gives players no incentive to deviate from their initial strategy. Next thing we need to find out is whether this game is this Nash equilibrium Pareto optimal outcome or not. By Pareto outcome or Pareto efficiency, what we mean, when the utility of one person cannot be increased without decreasing the utility of other, we say the situation has the Pareto efficiency. In this case, okay, if both the prisoners come in contact and agree to deny whatever happens, you can see when both deny, they get only 1 year into jail. Okay, if both confess, they get 3 years into jail. Obviously, getting 1 year into jail is better off than getting 3 years into jail. So here we can say this deny is Pareto Pareto optimal outcome. Optimal outcome. Okay, so we can say here that Nash equilibrium is not always Pareto optimal. In this case, Nash equilibrium is when both the persons confess and each gets sentence of 3 years into jail. But if somehow both the prisoners come into contact and decide to deny whatever happens, so both will get better off. So we can say this deny is Pareto superior to confess. Okay, confess. So as you can see, Nash equilibrium is not always Pareto optimal, as we have seen in this situation. So the irony of this prisoner's dilemma is that when each of the two parties act selfishly and does not cooperate with other, that is when both confess, they do worse than when they act unselfishly and cooperate together, that is when both remain silent. Okay, so when they both play selfish, they are worse off. Okay, when they are unselfish, they are better off. Okay, so I hope I make myself clear in this video. Thank you.